Welcome, everyone. The first speaker is Leslie Goldberg from Oxford University, and she's going to talk about phase transitions and approximating partition functions.
Okay, so this is going to be a survey, and I'm going to talk about, you've probably heard some work about approximating hard counting problems in connection to phase transitions. I'm going to focus particularly on the older work, and the idea is really to kind of just give the idea. So what do phase transitions have to do with counting, and how do they connect? And you should feel free to interrupt at any point, because it's supposed to be a survey, so yeah. Okay, so I'm going to start out and tell you what a partition function is. And a partition function is just a generating function for counting weighted combinatorial objects. Okay, so I'm gonna kind of define it by example, but you can view it pretty much as any generating function. And usually there's an underlying spin system. And these spin systems tend to come, for example, from statistical physics. And so I'm going to start out with just a very particular example, and I'm going to tell you about the so-called hardcore model. And the hardcore model, it's a model of a gas that lives on a lattice. And the different sites of the lattice can be occupied or unoccupied. Okay? So in my pictures, I kind of color a vertex if it's occupied, and I leave it uncolored if it's unoccupied. And basically, the idea in this model is that these particles, they take up a lot of space. So if they're too close to each other, they can't both be occupied. And so an edge denotes closeness. So for example, I can't have this one and that one both occupied. So configurations are independent sets. Okay, and the lattice wouldn't necessarily be bipartite, but I've drawn it that way for some other purpose, as you can see. Okay, so configurations are independent sets. So we've got some underlying graph, G, like that. And a configuration is just an independent set in the graph. And then what we do is there's a weight function. So sigma is a weight function, and if the independent set has k vertices, then the weight of this independent set is lambda to the k, where lambda is some parameter. So the weight of the independent set, lambda to the k, exponential in its size. Okay? And lambda is just a fixed parameter of the model. And then the partition function.
Should I think of lambda as small or big?
Okay, good question. So yes, should I think of lambda as small or big? Actually, we studied both. And but obviously for independent sets, lambda is 1. And for much of the talk, I'll be thinking of lambda as bigger than 1. But in fact, the whole phase transition thing is about how lambda changes. And, yeah. So, okay, so lambda's going to matter for us. But if you get worried, remember that lambda equals 1 is just independent sets, all equally weighted. And then the partition function, I'm sorry how low it is, but anyway, what the partition function is, if you can't see it, I'll just tell you, it's the sum over all configurations of the weight of the configuration. Okay, so we're just it's the generating function, yeah? So just keep enumerating all configurations by weight. And that's the partition function. So if I take lambda equals 1, the partition function would be the number of independent sets. Okay, is that good? Okay, so that's the model. Now, sorry, this is just a non-slide, so you can just close your eyes. I just wanted to apologize in advance to all these people whose work will not be discussed, and that's the whole purpose of the slide. But what I will tell you about is really some very early ideas and how the connections go. So I'm going to talk to you about some really, some quite old work about sampling independent sets, and that's going to set the framework. Then I'm going to spend a lot of time telling you about Alan Spry's work connecting phase transitions to approximation in the hardcore model, and then I might move on to the ferromagnetic Potts model and tell you some connections there. And there's a lot of interesting work, especially by the Georgia Tech team and guys at Berkeley, and with apologies to them, I'm not going to tell you about that, because my goal is really to just motivate the ideas. I want you at the end of the talk to understand what do phase transitions actually have to do with hardness of approximation, and then the fine details are later. Yeah? Okay, so I'm going to start by just backing up to optimization problems, because I think that's very familiar. And so this slide is supposed to be stuff that you probably know, and which we're just going to implicitly use, okay? So let's remind ourselves what kind of optimizations are hard. Well, certainly we know that it's hard to find a maximum independent set, and of course we all know because of PCP that it's hard to find a maximum, an approximately maximum independent set. Similarly, I think you know it's hard to find a maximum cut in a graph, or approximately a maximum cut. The one that you might not have seen recently, which we're going to rely on, we're going to look at a setup where you have a system of linear equations just over GF2. So the input's just going to be, you've got a bunch of variables, x1, x2, and so on, and I got a bunch of equations, xi plus xj is equal to 0 or 1, and okay, so the question is how many of these, okay, so it's easy to tell whether you can satisfy all the equations, yeah? But it's hard to tell whether you, how many you can satisfy simultaneously, what's the most you can satisfy, and in fact, PCP tells you that it's hard to get within 11/12 of the maximum. So this will just be something that we rely on along the way. Okay? Okay, so that's optimization. And now I want to start out by saying, what does optimization have to do with counting? So if you knew that optimization was hard, how would you find hardness for things like calculating partition functions? And so I'm going to start out with a kind of motivating example. And we're going to go to the simplest partition function there is, and I'm going to take lambda equals 1. Okay, so the partition function is just the number of independent sets. And what I want to show you is why is it hard to estimate the number of independent sets of a graph. Okay, and so to start out with, if I have a graph, it's easy to find an independent set, right? There's nothing about maximum. You could take the empty set, you could take anything, you know, it's easy to find one. I claim it's hard to estimate the number of independent sets, and actually we will just be able to see it immediately. So I'm just going to walk you through a little proof, and it's not very hard. Okay, so let's do that. So and I'm just going to talk. You don't have to read this. I'm going to talk through it. Okay, so we're going to start with a graph, and this is just an edge of the graph. And over here, the idea is you should be thinking of a graph where we want to find a maximum independent set, because we know that's hard. Okay? And what we're going to do is we're just going to blow up every vertex of the graph into a big independent set of size r. So this is u, it becomes a big independent set. And this is v over there, it becomes a big independent set. And then wherever I have an edge, I'm just going to make a complete connection. Just connect everything, yeah? So all I did is I took the graph over here and I blew it up. Every vertex became r vertices, an independent set, and every edge just became a complete connection. Okay, and now I'm going to have a think about this blown up graph over here. Okay, well, if you imagine the blown up graph, let's think about an independent set over here. Well, first what I want to point out is that an independent set over here would point out an independent set over there, yeah? Because if I have a vertex, a blown up vertex that's empty, that's out. If there's something in it, that's in. Okay? So from over here to there, I can make a map from independent sets over here to independent sets in the original graph. Obviously it's not 1, 1, so we're going to calculate that. How many ways? Well, if I take a size k independent set in the original graph, then that corresponds to 2 to the r minus 1 to the k independent sets over here, because every time I put a vertex in, I have 2 to the r minus 1 things I can do. But if I put it out, I just have to leave it out. Okay, so that size k independent set is 2 to the r minus 1 to the k independent sets over here. Okay, is that picture? Okay, and actually that's the only fact we need, and we'll be able, just in a second, to see that it's hard to count these guys. Okay, so here's the argument. So We know that if you have a size m independent set in the original graph, okay, obviously it's 2 to the r, I don't know why I changed the variable, it's 2 to the r minus 1 to the m over here. Now, what about smaller, say that's the max, say m is the max independent set. So if the maximum independent set in our original graph has size m, then over here we would represent that 2 to the r minus 1 to the m times. Now, there are other independent sets in the original graph that are smaller, but there's only a few of them. There's only 2 to the n of them, okay? And all of those 2 to the n minus 1 smaller independent sets, what's their weight over here? Well, each of those comes up at most 2r to the r minus 1 to the m minus 1, yeah? And so all I have to do is make r bigger than n, yeah? And the whole sum of independent sets over here, I get the ones that correspond to max, and then I get this puny little number, which is very much smaller, because it's, I multiplied by 2 to the n, but I divided by 2 to the r. Think of r as like n squared or something like that, yeah? And so if I could count the independent sets over here, even approximately, this stuff is just irrelevant. It really is approximating for me that number, and so I can find m. Yeah. Okay. So that's how optimization hardness gives us hardness of approximate counting. So immediately you can see that you can't approximately count independent sets, either exactly or approximately. Oh, don't do that. And okay, sorry about that. And even computing the log of the number of independent sets would enable you. Now, a lot of work has been done on figuring out how to do this kind of argument for bounded degree graphs. Because you can see, in order to play this game, I had to make r huge. I had to make it like n squared. So I would show immediately that approximating independent sets is hard in a graphs, but says nothing about bounded degree graphs. So that's the next step. Okay, so let's go now to bounded degree graphs and see what happens there. And the first people to look at this were Dyerkers and Jerem back in around 2000. And what they did is they studied what happens for independent sets in a random bipartite graph. So the idea is that we've got n vertices on each side, and we've got a rounded delta regular graph, and they studied what is the kind of setup for independent sets in this graph. Okay, and what they did is they studied this quantity E of alpha beta, and basically this is going to be the expected, because it's a random graph, the expected number of independent sets that have alpha n on the left and beta n on the right. So we want to get a feel for these numbers, so here we've got 7, n is 7, right? So 7 vertices on the left and on the right. And I've shown you a particular independent set where alpha is 3 sevenths and beta is 1 7. Okay? And E of alpha beta is how many independent sets over there like that. And what they found is that if delta is sufficiently small, then this quantity, E alpha beta, its logarithm has a single local maximum. So if you study this function, the log of E of alpha beta, there's only one local max in the whole function, and it has alpha equals beta. Okay, so what does that tell us? That tells us that a typical, so why did I take the log? I took the log because I'm interested in the number of independent sets of each type. And if the log has a max, let's take a global max. Suppose that I take an alpha beta, which is a global max of this function. Then that would have exponentially more weight than anything else if I just added them all up, right? Because it's the log. So if delta is at most 5, the log has a single local max, and alpha equals beta. So that's saying the independent set is quite balanced. That's about the same number on the left and right. Okay? But they found that if delta is bigger than 6, then there are 2 local maxes which have alpha not equal to beta and are actually symmetrical. So one of them has alpha big and beta small, and one has beta big and alpha small. Okay, so that's saying that as long as the degree gets high, then a typical independent set either has vertices on the left or else on the right. Now, if you think about it for a minute, this is what you would expect, right? If I start with a big bipartite graph, if I start throwing edges in, then eventually a typical independent set's just going to use one side. So clearly that's going to happen sometime. What this says to us is that it happens between 5 and 6. Okay, now, but this is really old work, so although we can see now, looking at it, that the phase transition happens between 5 and 6, they couldn't exploit that then, and the reason is that there's very little concentration. So in fact, we're going to come back to this in a minute, but what they used, in fact, was that when delta's a lot bigger, actually 25, so when delta gets up to 25, then what happens is, with all but exponentially small probability, one side is basically empty. It has almost no vertices in, and the other therefore has about half of them. So once you get big enough, you get some concentration. One side has a very small fraction in, I'm afraid I'm reading lambda, that was a bit bad, but anyway, some constant fraction in, and the other side therefore about half and half. Okay, so this is, well, first what I'm going to do is I'm going to tell you how they use this to show hardness of counting for graphs of degree at was 25, and then we'll come back and we'll look nearer to the real phase transition and try and get the right answer. Yeah? Okay, so 25. So we're going to stick here with the, so they were doing lambda equals 1, so independent sets. And here's the result that they get. So they say unless RP equals NP, there's no polynomial algorithm that estimates the log, and we're going to come back to that, of the number of independent sets of a delta regular graph, delta bigger than 25, within some small relative error. It doesn't really matter, just something small. Okay, so that's the kind of theorem that they got. One remark. They showed it's hard to estimate the log within 1 plus or minus epsilon. And of course, that's interesting because that's a really crude approximation. So that's like saying estimating the partition function z within a factor of z to the epsilon. So this is an exponentially big quantity. So you're not able to get even within an exponentially big factor. Okay? And we're gonna come back to that because this changes it in some context. Okay, so let's and again, it's great to start with the old stuff because by the time time passes, it seems eventually easy. So this is now easy. I can just show you this. This is so let's do that. So we're going to start with systems of linear equations, and we just talked about the fact that if I gave you a system of linear equations, that it's hard to tell how many you can simultaneously satisfy. And just like we went from finding a big independent set to counting independent sets, now I'm going to go from finding a big number of satisfied equations to counting independent sets. And we're going to use the same kind of trick that you just seen. Okay, good. So how do we do that? So we're going to make so we're going to have an input, which is a system of equations. We want to show how many can be satisfied, and I want to reduce that to counting independent sets approximately in a degree 25 graph. Okay, so here's how we're going to do it. So for each variable, there's a variable, I'm going to make a gadget, and the gadget is just going to be a delta regular bipartite graph. So it's going to be exactly one of these that we were just looking at. Okay, so just showing. So this picture, which you'll see coming up on the next few slides, it just denotes a random regular delta regular bipartite graph. Okay, and just to give you a kind of clue about what's coming next, we know a fact about this, right? We know that in a typical independent set, one side will be almost unoccupied, and the other side will be about half occupied, and I've colored it green. It could go either way. They're both equally likely, but nothing else is very likely. Okay, so that's what we know about independent sets around the graphs. Okay, so for every variable, we make one of those gadgets, and now we just want to code up some linear equations. So let's do that. So if we have a linear equation, xi plus xj, and we try to make them the same, then we want to make them the same. Well, obviously I've got two states, right? I've got green on the left and green on the right. And so to try to make them the same, all I do is I make a big matching. And I take some of the right here to some of the left here, and vice versa. And that'll encourage the two variables to align the same direction because, you know, if the right-hand side is unoccupied on both, then the matching edges are no trouble for me, right? They're not causing any trouble at all. Each of these can still be in with about probably half. Okay, and if we had an equation like xi plus xj is equal to 1, we just align them the other way, because now we like to encourage these two variables to be different, so we match left and left and right and right. And once again, if they do what we want, if they align out of sync, then the matchings don't cause us any trouble because these are all unoccupied. And so over here, every vertex could be either unoccupied or not. No problem. Okay, so, all right, so I guess I just said this. So typical independent set, every variable has one side very empty and about half with neighbors. So we can put them together like that. Well, let's just move on and add them up, and it's very easy. It's just like the independent set thing. So let's look at what happens. So first, what is the picture I've drawn for you here? So I've got variables xi, xj, and xk. And in our example, I've put xi in the 0 state because the occupy is on the left. I've put xj in the 0 state because I put the occupied guys on the left. I put xk in the 1 state because I put the occupied guys on the right. And we're just going to look at this example and see what it contributes. Okay, so I have two constraints. I have the constraint xi plus xj is equal to 0, so that's what these red matching edges are for. I also had a constraint xj plus xk equals 0, and so that's what the blue edges are for. And now I want to just, and obviously there will be more constraints in the general system, but I just want to talk about what happens here. This constraint is satisfied, right? Because xi and xj are both 0. And I claim that because it's satisfied, there are, if I put m edges here and here, then there will be 4 to the m choices for how to fill in the independent set, because these are on the out. These are out. But I get about 2 to the m choices here, and then I get about 2 to the m choices there. Yeah? Does that make sense? Questions? Yeah, I got m edges here, and I got m edges here, and this side is out because the gadget is in that state. This side is out, and now I'm saying how many ways can I now, how many independent sets are there now? This vertex can be in or out. This vertex can be in or out. This vertex can be in or out. So I get 2 to the m choices there. And then again, I get 2 to the m here, so I have 4 to the m in all. Okay, but now let's look at the vertices involved in the xj plus xk equals 0 constraint. And what happens here is that this constraint's not satisfied, right? Because this guy is 0, and this guy is 1. So they're not the same. Okay? And so nothing happens here. These guys are just out. These vertices are out. These vertices are out. But if I look at these vertices here, there's an edge between them. So let's look at this edge. The endpoints of this edge could be in, out, or out, out, or out, in. So I get 3 to the m choices. Is it? Yeah, I know the schematics are really high level, so it might be. This is a blob. This is a bunch of vertices, yeah? And this is a matching of like that. Does that make sense? So we get 3 to the m choices here. So the point is that if the constraint is satisfied, I got 4 to the m choices. If it's not, I got 3 to the m choices. M is in my own control because I can build these matching edges. Okay, so that's good because now we're basically done. We just have to sum up because if we look at an independent set here, it's very, very, very likely that all the gadgets are well behaved. They either go left or they go right. They don't do something else because that's exponentially unlikely, so we can forget that bit. Okay? So all the gadgets are well behaved. So I do have a kind of assignment of the Boolean variables, namely the ones that have green on the left. Okay, so I'm going to call that S. That's going to be the set of variables that are true in a linear system, or that are zero in a linear system, yeah? All the ones that go left, those are zero in a linear system. And now we can just add up how many independent sets there are in this big thing. And, well, it's the sum overall S, so all choices of where the green live, of the number of independent sets that are compatible with that. And we know that the number of independent sets compatible with that is 4 to the m times the number of satisfied constraints, times 3 to the number of unsatisfied constraints. Okay, that's the calculation we just did. And now, the whole point is just the same as before, that m is huge. M is huge. And if you don't satisfy a constraint, you lose a factor of 4/3, right? Because you could have had a 4, but you get a 3. And it's 4/3 to the m. M is huge. So if you looked at this sum, if you looked at an S that wasn't satisfying as many as possible, it's negligible. It's doing nothing, right? It loses because of this big M. And there's only a few of these S's, 2 to the M, like before, nothing, because M is so big compared to M. So if you look at this sum, you might as well just sum over the ones that are maximizing. And so once again, if you could estimate the number of independent sets, you would know how many were satisfied, yeah? So you could, even if you could estimate the logarithm of this thing, you can kind of see by looking at it, you would be able to work out how many of these equations did you actually satisfy. Okay, so that's the whole game. Okay, so that was Diaphragms and Jerem. And the next question people wondered is, what was the right degree bound?
Sorry, how is the graph delta regular?
Sorry, how was what?
The graph is delta regular, you said. So you said m is huge. Oh, because the equations start off with this.
Yeah, so I probably overloaded n, but let me, my goal is to make everyone understand, so let me just make sure I do that. So I've got some number of equations. Let's call that, I don't know, E, for number of equations. That's part of the input, okay? Now I build this thing, and I've got a regular bibar chart graph, and for each side I get capital M edges. For each equation, I build one of these, like these red edges, where I have M and M. M is in my control, and I'm going to make M really, really big compared to E, the number of equations. And then the point is that so there's not many truth assignments, because it's 2 to the E. But M is E squared or E cubed or something like that. And so failing to satisfy an equation really, it just contributes negligibly to this sum.
I was just wondering about the graph in constant degree, but is that because there's sort of linear equations to start off with?
How does the graph get to be constant degree? Good, okay, sorry, I misunderstood the question, but the way that happened, which I probably, what my picture attempted badly to indicate, is that you only use these vertices once. So when I put an equation in, I use the red ones here, and then I'm never going to reuse those. They've got a degree delta gadget, so they got 25 there, and I've given them degree 26 because of the red edges, and then I won't reuse these. The next constraint I'll pack in here. So every vertex is involved in its 25 regular gadget, and then it's involved in one of these edge things. Yeah. Any more?
So the only place where you used randomness was in the constructions of these gadgets. Is that the only place?
That's right. Right, only in the gadgets. That's right.
And we don't have deterministic constructions of these.
We have deterministic constructions. I mean, it's more or less just counting, right? No, I mean, I don't know of any deterministic constructions, but there's no reason why you couldn't have one, because it's just about, yeah, it's about the properties of the gadget. Yeah. That's right. Okay, so that's anything further? Okay, so that's degree 25, and then what people were wondering after that is what's the right degree bound? Okay, because we already kind of saw the hint that the phase transition should really happen between 5 and 6. But to address this question, I want to go back to the hardcore model. So you remember the hardcore model, all I did is I weighted the independent set, so that an independent set of size k has weight lambda to the k. And now we're going to go back to that. Okay, so we've been looking at lambda equals 1 for a few minutes. We're going to go back to general lambda, but okay. So configuration of an independent set, oh, it's right here in front of me. If it has k vertices, the weight is lambda to the k, and the partition function adds those guys up. Okay, so we're going to go back to that slightly more general framework. And the next thing I need to do, is I need to talk a little bit about running, so this model is the model we want to consider. We very much want to consider it on finite graphs, because that's what we care about. But in order to understand it, it's going to be easy to have a little digression into this thing on infinite trees, and that's what I'm now going to do. So we're going to talk about the same model, but we're going to talk about it on an infinite tree, and I'll have to tell you a little bit what does it mean. Yeah? Okay, and then we'll come back. All of that is just by way of getting the right answer in the finite case. Sorry, I keep switching the slide, but I realized one more thing I want to say here. This model, I want to just change, I want to generalize it a tiny bit, and I think you'll be able to see it makes no difference. I have a graph, and I've got all this stuff. What I also want to allow myself to do is to condition on a few vertices, which I'll call the boundary. Like, I'm going to insist this vertex is in, I'm going to insist this vertex is out, this one is in. I'll allow myself to just pin a few of them and insist. And you can see that it wouldn't really change the model, because if you want to insist that a vertex is in, well, fine. Just take its neighbors out, multiply by lambda, and work on the smaller graph. It's the same thing. If you want to insist a vertex is out, fine, just delete it. Okay, so it really makes no difference. But I just wanted to make that observation so that it doesn't trouble us when we get to the infinite case. Okay, so now, we've got the hardcore model, and I need to move slightly more towards a probabilistic way of looking at it. And so first I want to tell you what the Gibbs measure is. And the Gibbs measure of the hardcore model on a finite graph is just the natural probability distribution associated with the partition function we've just looked at. So in the Gibbs measure, the weight of a configuration sigma, the probability of a configuration sigma, is its weight divided by the whole partition function. Okay, so it's just the induced probability distribution. Now, I want to tell you what a Gibbs measure is on an infinite graph, and I don't want to do it formally, or I hope you let me, I don't want to divide it, I just want to give you an idea. So Gibbs measure on an infinite graph. So if I have an infinite graph and I've got the hardcore model, I can talk about the model there. I can put a measure on configurations, which are just independent sets. It's a Gibbs measure if the following happens. Suppose you look at this infinite measure, and then you look at some finite region, some connected finite region, say. Okay? And now, what I want to do is I want to sample the boundary of that region from the big infinite measure. Okay, so I just want to look at the induced measure on this finite boundary. Do that. And then, now let's look at the finite piece surrounded by the boundary and see what's the induced measure on that. And it's a Gibbs measure if it's exactly that. Okay, so we know what it means for the distribution on the finite piece to be this. And an infinite measure is what we want if it just induces that under the finite piece. If that didn't make any sense, then maybe fewer words is better. It's a measure that if you look at it in any finite piece, it's just what we want. Okay?
So in this infinite graph, vertices can have infinite degree, or
Yeah. Let's say no. In fact, let me just say no. I prefer, yeah. And then we're never going to do one of us. So, yeah. It is well defined, but not, yeah. But we don't. Okay, good. So we got a finite, an infinite graph with degree, finite degree. Okay, and is that kind of, it's not meant to be, is it clear enough that we can just, okay, now, it's usually true that there's a Gibbs measure. That's not usually hard to see, but there can be more than one, and I do want to talk to you about that, because that's what's going to be important for us, okay? So, and I think it'll get more clear, actually. Because what I'm going to do is look at it, the delta regular infinite tree, and actually that's the only infinite graph that we need. Okay, so let's look at the delta regular infinite tree, and I'm going to talk about the hardcore model. And I guess I've drawn delta equals 4, so here's the infinite tree. And what these squares mean is just that I didn't keep drawing, obviously, but it is an infinite tree. It doesn't stop here. Yeah. Okay, and let's first look at a particular Gibbs measure that always exists. Okay, so I'm going to show you a Gibbs measure that exists on this tree. Okay, and so what I'm going to do is I'm going to look at the occupation probability at a vertex in the tree. And so I colored that guy red, so we're going to think about him. And I want to try and calculate what his occupation probability would be. And I know this is completely non-rigorous, but we're just going to do it anyway, so you're probably going to let me. So what I want to do is I want to think about this infinite tree. Let's suppose that we knew below him, from below, what's the occupation probability of the vertices below him, okay? And I'm going to define a quantity, again I'm using variables, sorry, but I'm going to define a quantity m, which is 1 minus p to the delta minus 1, so it's like looking from below the probability that all these guys are unoccupied. Okay? Now, let's try to calculate the probability that this guy was occupied. Well, if all the guys below were unoccupied, we could, he could be occupied, in which he would contribute a weight of lambda, or he could be, so that's one possibility. In fact, that's the only way he can be occupied. And in the denominator, well, that could happen. They could all be unoccupied, and then he is occupied, or else he could also not be with a weight of 1. But also in the denominator, it could be possible that these guys aren't occupied. I don't know any way to make that higher. Can you see this? Oh, okay. Okay, so we can write this equation, and don't worry about, yeah. Let's just say this. Suppose you wrote this equation, and then you solved it for p. Okay? Forget about the kind of bogus way I was justifying the equation. What you can see is that if you solve this equation for p, that would be a Gibbs measure, right? That is clear. So my way of introducing it was kind of a little bogus, but once you get the equation, you can see that if you just solve this equation for p, that would be an infinite Gibbs measure, yeah? Because every vertex has occupation probability p in the whole tree. Does that make sense? Okay, so that's a Gibbs measure, and that's one that's always there. We can't get rid of that. That guy's always there. And it's called translation invariant. That just means that every vertex has the same occupation probability. Okay, so that's one Gibbs measure. And now I want to tell you about other Gibbs measures you might have in this tree. Okay? So the way I'm going to do this, don't start reading all the symbols, but let me just tell you a little bit about the picture at the top. Another thing we might do is, in fact, I want to just put it back for a second. So let me talk about another kind of Gibbs measure we might have. What if lambda were really, really, really big? Okay, huge. If lambda were huge, then a typical configuration would have as many vertices in as possible. Yeah? Now, how would you get a lot of vertices in? You would have to layer them, wouldn't you? Because if you had a tree, a delta regular tree, think of delta as 4 or whatever you like, and now I give you a huge lambda, and I say, what does a typical configuration look like? Well, lambda's big, so a typical configuration has a lot of occupied vertices, and the best way to get a lot is to pack them, odd levels, even levels. So yeah? Okay, so that's motivation for a second Gibbs measure that can exist. And what I've done now to this tree is I've labeled the levels plus for even and minus for odd, I don't care. I labeled them to indicate that the levels have a parity. And now let's look at another kind of set of equations that I could have shown you for getting a Gibbs measure. So let's suppose that P minus is the occupation probability of a vertex at the minus level, and P plus the occupation of a vertex at the plus level. And then if I look at a vertex on the minus level, the probability that all his children are unoccupied is 1 minus P plus delta minus 1. And so the equation for P minus is, I get lambda times this thing I'm calling m plus divided by the denominator. The details aren't very interesting. It's the same as before. I just decorated with pluses and minuses. But the point is that instead of having one equation, I've got two mutual equations. And if you solve them together, well, one solution you could get is the old one. P minus is P plus, so why did you give me all these equations? But another thing that could happen is that you could get a solution where P plus and P minus are different. Right? Maybe P plus is bigger. And that's called a semi-translation invariant Gibbs measure because all even level vertices are the same. Okay, and that thing doesn't exist. And whether it exists or not depends on lambda and delta, and we're about to see more detail about that. Any questions? Cool. Okay, so now I'm finally answering the question about where lambda lives. The truth is that there's a critical value of lambda which depends on delta, and this happens to be the critical value. So the critical value of lambda is delta minus 1 to the delta minus 1 divided by delta, it doesn't matter, delta minus 2 to the delta, that's the critical value. And the truth is that if lambda is below that critical value, then we're in a world which is called uniqueness. And what uniqueness means is that there's exactly one Gibbs measure, and it's the one where every vertex has probability. So that simple equation I showed you first, that's the only Gibbs measure that exists. Okay, so that's true. That's all there is. But if lambda is bigger than lambda c, then these two semi-translation invariant distributions, they also exist, and that's called non-uniqueness. Okay, so that's how the world works for the hardcore model on the tree, is that there is this threshold, and if you go from the one Gibbs measure to that.
And there's nothing else
And there's nothing else. That's
in this.
no. There may well there may be. You're asking whether there can be other Gibbs measures. Yeah, I'm not claiming there can't be other Gibbs measures. But what I'm claiming is that in the uniqueness range, there's just the one, and above this point, those two also exist. Actually, I don't think there are others, but I don't want to make that claim in case I'm lying or something. Yeah.
The Gibbs measure has the threshold point somewhat different from.
Oh, very good. So that was a question about the threshold point, and here for hardcore, it's okay. The threshold point's okay. It's in uniqueness, but there are a lot of these models where the threshold is still open, and so there are a whole lot of these models where we have a picture just like this, except for the threshold's a bit confusing. But here it's okay. Okay, so now, 5 minutes, okay. Okay, so now what I want to do now is talk about, so I was talking about approximation, and then I went off with this uniqueness, and I want to, in the last 5 minutes, tie it back and show you what did that uniqueness actually have to do with the approximation. So there's this excellent result by Dror Weiss in 2006, and what Dror showed, which is really actually a great result, is that you can approximate this partition function as long as you're in the uniqueness regime. So I'm going to talk about this for a bit to make sense of it for you. So what I've shown you here, this was about an infinite tree, the infinite delta regular tree. We used the infinite delta regular tree to define this uniqueness quantity, but now what I want to do is forget about the tree, because I don't have a tree, I've got a finite graph G, okay, but it's got degree plus delta. And what Dror showed is that if I've got a graph with degree at most delta, and my lambda is in the uniqueness regime, then I can actually approximate the partition function. I actually can tell you a little bit about how it actually works. Yeah? So let me do that. So here, just I'm going to do it really roughly. In fact, I don't even know what that says, so don't read it. I'm just going to tell you, okay? Okay, so here's how you approximate the partition function. So first, I want to convince you of this fact. Suppose I could take a vertex of my graph and I could work out the probability that it's occupied. That's the whole job, right? Because if I could work out the probability that it's occupied, say I figured out that it was occupied with probability of a quarter, then what I could do is now force it to be occupied by putting it in and taking its neighbors out. That's a smaller graph. Calculate the partition for the smaller graph and multiply by 4 because of the quarter. Yeah? So if I could estimate the probability that it was occupied, as long as it wasn't exponentially small, which it isn't, so don't worry about that, it's no problem. That's the whole job. Okay, so now let's talk about how do you estimate the probability that a vertex is occupied. Now, one thing you could do is you could take the vertex and consider all of its neighbors and all of their neighbors, and you could make a tree, much like our infinite tree, and you could try to calculate, you know, if all these guys are in and these are out, and then if you take the tree to its whole depth, you could try to calculate the probability that this guy's occupied, yeah? And actually, you don't need kind of cycles. Like if you start unrolling the graph, I don't have time to give you the details, but I think you'll agree it's not so surprising that if you put the right boundary conditions on, you can go ahead and truncate when you revisit vertices and you can calculate this tree. Now, of course, I've got a tree, and that's exponentially many possibilities. If I say occupied, unoccupied, that's too many. Okay. Now, what Drawer noticed is that if you're in uniqueness, then what that means is that correlations between vertices, they don't last very long. Like if you've got two vertices far away on the graph, they're not very correlated. And so if I took this tree, this nominal self-avoiding walk tree, which I would use to calculate the probability that the vertex is in, I could just truncate it at depth log n and just fix the whole boundary out. And it wouldn't really have much effect on the root, because log n is so far away from the root that conditioning makes almost no difference. Okay, so that's the point about uniqueness. Correlations die quickly, and so you can do it. Now, because I've got about 3 minutes, right? Yeah, so now, 3 minutes, I'm going to do the other side. And the other side is by Alan Sly. And he shows, just in a nutshell, that as soon as you leave uniqueness, it actually becomes hard. So that phase transitioning the infinite tree, that's exactly the barrier between easy and hard. Alan Sly's proof will be able to do it, and we won't do the proof in 3 minutes, but he goes back to Friesen-Jerom's gadget, okay, so which we've already seen. And now, the point is this. Let me just go back to this gadget. We know from before that if the degree was at most 5, that there was a single local maximum. We know that if the degree is at least 6, that there are 2 local maxima. Those are like the P plus and P minus in our tree. Now, the point is, that's true. So there is a phase transition here, but these leaves, these vertices, are very, they're still very correlated. They're not very independent. And so what Alan Sly does is he takes this graph. Well, I'll give you one more slide. Okay, so here's a picture of his gadget. What he does is instead of making it degree 6 everywhere, he makes the gadget degree 5, so a 5 regular bipartite graph. And then down here, throw in another matching, so most of it is the 6 regular bipartite graph, because it's supposed to be looking like the Friesen-Jerome thing. Then he attaches 5 area trees, like this, and the whole purpose of the trees is that these endpoints are going to be independent of each other. And, okay, what's the point? The point is that the gadget has a phase, just like all the ones we've seen before. With high probability, you get the green here, or else you get it there. Okay? However, what these trees do is that they give you independence on the vertices out here, And so let me just tell you what happens with this gadget is that if it's in left-leaning mode like this, that's like, these guys are like negative level vertices in a tree. These guys are like positive level vertices, okay? So and they're very independent of each other. The only other thing that's likely is that the green sits here, and then these guys are negative and these guys are positive, and they're very independent of each other. So what we've built is this very robust gadget where these terminal vertices, they are correlated with each other, but they're only correlated by the phase. So if you condition on the phase, they're independent of each other. And I know I'm running out of time, but that's exactly what you need to put together, just like the linear equation proof. You can build a proof much like that, except for, so I happen to use max cut. And that shows the hardness there. So the situation then is that if you're below critical, then you can have an algorithm, and if you're above critical, then you've got hardness. And just to close, I want to point out that there's all sorts of interesting issues that come up, because, for example, actually there's a result by Sly and Soon that show that this is true even assuming the log of partition function, just like the things we've seen. But for example, if you go to the planar case, suddenly estimating the log becomes easy, but then there are still ways that it could be hard, and there are other spin systems and a lot we don't know, but I will stop.
We have time for a couple of quick questions.
So was it actually White that thought about the Gibbs measure on the infinite tree as part of his work, or was that known in some other context?
Oh, yeah, I mean, the Gibbs measure on the infinite tree was already really well studied in the physics literature, because they really care about that. So there's loads of work that is about Gibbs measures. But interestingly, for some of these more exotic, so for the hardcore model, in fact, the critical point goes all the way back to Kelly, really early, I don't remember when. But in any case, there are a whole lot of spin systems like the Potts model and things like that, where some of these critical values aren't even known in some of these models. So the hardcore models really they understood, and that's partly why I decided to use that for a survey. But there are cases where, well, we don't even know.
Are there any techniques where we can show something better than NP hardness? Because the simplest permanent is probably one of the simplest generating functions, right? And then
better than NP hardness, yeah. So for example, for the top polynomial, we have number P hardness almost everywhere of approximation, just kind of by bisection. So the question was, can you do better than NP hardness? And the answer is that not for things in NP, right? Because for things, actually that's an important point. So if you're approximating a function in NP, then of course you can't do better than NP hardness for that, because by Valiant Nazarani kind of bisection, you can do it with an NP oracle. Okay, so approximation within NP, that's only NP hard. You can't have it more hard. But all these models that I didn't show you, a lot of them have parameters, and the parameters can be complex or negative numbers and things like that. And as soon as you put those in, you exit NP, and yeah, then you can get hard. You can get more hardness. But I know the permanent, of course, is harder exactly. But I'm saying that for approximation, we can't do harder than NP if it's in number P.
Well, maybe I can ask. What about at exactly the critical point here? You don't have either the polynomial time or NPR.
Not in this algorithmic case. That's right. So it's still up to the boundary that. So what I was answering your question before was about the uniqueness. But you're right. There's a gap there.
Okay.
And actually, that's true. All these two-spin results has all these results about two-spin systems, and most of the boundary is open actually.
What's the conjecture? Hard or easy at the...
Oh. Yeah, I'm not sure.
Okay, let's thank Leslie again.